meeting room, I think. Okay. So good afternoon. So hope you have gone through the slides that I shared for last two lectures. Now today, first I will be recapping some what we learned before, and now then I will go to the next step of my presentation. Okay. So I would prefer if you switch on your videos whenever you if you have any questions, so please switch on your videos so that I can interact that student, and that this is the person who is asking me. Otherwise, by name it is very difficult for me to understand. So so it would be better just switch on the video once if you have any questions or something like that. So let me share my screen first. And from the previous lecture, anyone has any question? Of course, I will repeat. But if you have any question, any doubt, you can clarify and tell me that first. No question. Okay. So actually, in my last lecture, I let me see. Can you see my screen now?
I have one question, not
Yes,
regarding
please.
the course material, but regarding the logistics of the project from your part. Like, how will that work?
Mm, logistic from the project means I don't get your point. Means
Like in for the part where Kalyani ma'am is teaching, she has formed group of 8 people, and we'll be
mm-hmm,
doing the project in the classroom itself. So
mm-hmm.
how will it work for your part? Is there a
Actually,
project component?
of course, there would be. After today's lecture, actually, I am planning to give you some assignment, and with the same group, it would be means you will be doing with the same group. I think she formed a group with 8 people per 8 students per group, right? Or five,
Ye- 8 students.
eight students per group. That would be fine for me. Means around 85 students you have. So it would be 10 assignment I will be giving. So you have to solve those problems, mainly the problem solving. After today's class, actually, you will be getting more in details what kind of problem, what kind of assignment could come from this. So if let's finish today's class lecture, then you will understand what kind of problem I can give you. So I will assign few problems, maybe no, not 8 problems or 10 problems, but maybe 2 or 3 problems I will assign. You can choose any one of them, and you have to solve those problem or assignment. You have to solve through, and you will prepare some presentation and will present from the group. Is that okay? Does that clarify your question?
Thank you so much.
Okay, that is my plan. Yeah. And maybe I hope that after today's lecture you will get some feelings what kind of assignment could come, and what to do for that. Means you can do it on your means the two component, these courses has two component, at least from my part. One is the theoretical part, what that you can do by paper and pen, and the second component is the coding. Means you have to know. I hope last in my last class I asked these questions. How many of you know coding? So at least basic language, it is essential to know any language. Means it is not essential that you have to do in Python or in MATLAB or R. Any language is okay, fine. Even in C or C++, anything is okay. But I will give you some assignment that you have to solve. Means in a group wise you can do, you can discuss and you can consult, and but you individual has some their own opinion as per their result. Whatever result they will be getting, individual should have their own opinion. It is not that 8 people in a group, so 8 people will give me the same answer, same result. of course the result would be the same. If it is from mathematics, so result would be the same. But it could have, you can explain the problem, you can explain, your analysis could be different. So that I would be expecting from your from that assignment, from this session. Is that okay? So
Yes. Thank you.
by the who are you means, I can see you means whenever I'm making it in full screen, I can see anyone. So it's difficult
I am
for me.
Aryan. There is actually a
Okay,
problem
Arya.
with my camera. That's why you cannot see me.
That's okay. That's okay. That's fine. But just mention your name. It will be easier for me to catch you. Okay. Whenever you have any questions, any question. Okay, let's start then. For today's lecture, I hope you spent quite a good time, a long time, 2 lectures and you got about 3 weeks time to go through all these lectures, lecture notes. So I will recap this thing, mainly competing hazard that already I described in my last lecture, but again I will come back because this is the most important factor to know for developing a model for mathematical modeling. And last day I'm not repeating the boxes and arrows. This will continuously coming while will I explain the other things, that competing hazard or force of infection, these terminology when I'll be explaining. Automatic, that box and arrows, the basic things already I described in Blackboard, so you know those things, I am assuming. Now then the next step was the force of infection. In the force of infection, what is force of infection, how to construct, how to calculate that, how to form the model, how it acts in the model, that I will show. And the next step would be the basic reproduction number. I mentioned about this terminology, but I will go in details, means how to estimate from model, how to do these things, how to measure this quantity from model. And more complex, I will not go to the more complex model, that will come later stage. So I'll go again some different kinds of models. After today's lecture, I am expecting that you will be able to develop some at least basic models, how to form models on. And you can, if you go through any of the papers, any research papers in this area, you can understand, okay, this is the way, this is the mechanism, how they form these models, how they before analyzing them. Okay, you will be reaching up to that stage. That is my expectation. And today again, one more thing I should clarify. So I am expecting that everyone has their own laptop. You are in front of laptop or PC, and I will provide some example problem that you have to solve by yourself, and then continuously I will be going through that. Means I will show, of course, the results, but you have to do simultaneously 5 to 10 minutes depending on the problem. Then you have to, because I have 3 hours time, I can do these things, means so that hands-on training, you can say, so that you can do this thing, you can understand properly. And we will go, if you have any confusion, we'll go from my side, I will show the result, and we'll analyze them, I will describe them. And some of you actually had already sent me in mail the assignment what I was there at the end of my last presentation, last talk. Some of them have already shared to me. Thank you for those who shared those answer script. So I will go through all the problem. Now, what kind of problem means, through that actually I understand what is the problem of understanding, means there might be some gap between me and you students. So that gap actually, if someone submit the assignment, then I can really easily understand that this is the problem, so I should explain this way, so I can improve my teaching quality as well. If you respond according to a problem set or your question set, then I will try to means go in that way actually. So I will come to those points now, those questions. First I will be starting from that cohort model. This is called cohort model. What is cohort model? You have some cohort, some of the population, and say here some infected cohort, infected populations are there in a single box. You remember that box and arrows. So in infected cohort, there are say some 1,000 people in this cohort. Means initially there are 1,000 people in this cohort. Now they are recovering, they are infected with some disease. Now average recovery period, say 10 days. The same example I explained in the class room. So if average recovery period is 10 days, that means at what rate they are recovering from the disease. Average recovery rate. What is that? That should be the value of gamma. Here the indicated infected eye to recovered R. There is an arrow, and at the top the Greek letter gamma is written. Gamma indicates this is the rate at which that infected people are moving from that box to that next box. That means recovered box. So if gamma, if recovery rate is 10 days, average recovery rate is 10 days, what does it mean? What would be the value of gamma? Anyone can answer it.
So 1 upon 10.
1 upon 10, what would be there should be a dimension. It is not dimensionless quantity.
The day inverse.
Per day. That would be the rate. With that rate, infected people are moving to the next compartment. Now, actually, this is the assignment that I gave means at the end of. I didn't mention details because I didn't get much time to explain this in details. So I allow you not to. If you don't know, that's okay. I will explain this thing today. Then in the next time onwards, I would expect that you will give me the answer sheet, means the results, and I will discuss in the next class again. So these are the problem set. Means one was this, that we are looking a cohort of 1000 currently infected people and no one has recovered so far. I mean, no one is in the R compartment. Initially, all 1000 people are in the same box, I box. Okay. The average duration of infection is 10 days. That already you told me. That means gamma equal to 0.1 per day. Now we want to answer the questions. How many people will recover from infection over a 4-week period? You have 4 week means 28 days. In 28 days, how many people? Though recovery period is average recovery period is 10 days, that does not mean after 10 days everybody will be from I will be reaching to the R compartment. Average rate is 10 days, means the way it transit from one box to next box is, we assume normally in terms of differential equation, if you write the term that the rate of transition will be exponential decay. So from I to R. So after 4 weeks time period, means after 28 days, how many people will be going from I, means how many will be in the I box till then, and how many will be in the R box. If you get that answer, then accordingly you can answer all these questions, subsequent questions based on the output. How many people have recovered after 4 weeks? That is the first question. What proportion of total population does this correspond to? Second one is based on the plot. You have to plot this on your machine. At what time point were infected and recovered individuals equal in number? Then the next question was try varying gamma, means recovery rate. If recovery rate instead of 10 days, average recovery rate, if that is say 20 days, then you can see from your model how it shows. Means you in the model result, in the model plot, if you plot I and R together, you will see how recovery rate. If recovery rate is much higher, then that means it means the value is higher. That means recovery, it is rapidly recovering. Means people are going from I compartment to R compartment very rapidly. You will see the exponential growth in the R box and exponential decay in the I box. You can see these things, how it is changing. Means the feelings, unless you do this thing by yourself by writing a code, you will not get the feeling of how it is changing, how the rate parameters is affecting the system, that infected and recovered system. And I should say, according to for this course, is that the modeling or the mathematics that we learn in this course is not much difficult at all. The very simple mathematics we'll be doing, but the concept is important. You can learn very complex mathematics in any other classes, in other courses, but here the mathematics will be very simple. but the concept, the idea, what is happening, what parameter indicates what, that is important here. That relation between parameter and the actual scenario in the real life scenario, that interpreting all these two is very important. So that's why I'm asking you to do these things, these kind of experiments, that how varying gamma, how it looks like, the figure looks like, so that from the figure itself you can get some inference. Okay, this means this. And then last question is, what changes do you observe in the transition to the recovered compartment if gamma is higher or lower? So anyway, one after one, I will first for the first question, I will show you my results first from this side, from my side. Then you will, from the next question, you will try your side. I will give you some time for this, and we will go. So as you know, we have two compartments, I and R, infected compartment and recovered compartment. So we can we try to draw this diagram, diagram either here or in paper anywhere. You can do this I to R with and recovered it is gamma. Now the equation, shall I explain the equation again, or I think it is clear? Okay, let me repeat it. So number of people there in the I compartment or I box are moving from I to R, and the rate of transition from I to R is represented by di dt, right? So I indicates the number at a certain time t, how many are there in the R box. And these peoples are moving at a rate gamma. That means in terms of equation, while I'll write this, that di dt means I is changing over time, I is actually decreasing over time, I should say, at a rate gamma. So we can write this as di dt equal to minus gamma into I. Here gamma is the rate parameter. This is a parameter for any transition. Rate parameter is important, means in the model formation, whenever we will develop a model, we will give one rate. So that rate parameter is important. That indicates how fast it is moving from one box to another box, or how slow it is moving from that box to next box. So di dt equal to minus gamma into I. And the number of people they are moving and they are going out from one box must be compensated to, means they are entering in another box, next box. So the gamma minus gamma I that is coming out from the I box will be entering in the R box. So dr dt, rate of change in R, means their growing population is growing there in this box. So dr dt would be gamma into I. The remaining means that is going the proportion of people they are going out from this box, they are entering in the next box dr dt. So the set of equations is di dt equal to minus gamma I or dr dt into gamma I. Here the assumption is the total population remains constant, means our initial assumption means there no one is dying anywhere, you know, from the infected compartment or recovered people. People are not dying due to this disease. Only we are considering that cohort of population who are infected and they are recovering at a certain time at this rate. So formation of development of model structure and model equation, is it clear? I think already I explained in last class. If you have any doubt till now, you can tell me, ask me. Given that initial population size in the I box is 1000, and means in the infected box, means infected population is 1000. Now average duration is 10 days. I said I'm repeatedly saying the same thing. So after 4 weeks time, what would be the number in each box? How can you solve this? There are two approaches. One approach is easier, means easier for this scenario. It is easier, not everywhere it is not easy. Analytical approach, and another one is the numerical approach. What is analytical approach? What is numerical approach? Analytical approach means where you can solve the equation by paper and pen easily. So dx dt equal to say dx dt equal to some constant c. you can easily write the solution x equal to c times t plus some constant, right? That would be the there is analytically you can solve this. Okay, but there are some it is not easy to solve all the equations analytically, all different kinds of coupled equations specifically. This one, the set of equations I showed here, this is also coupled equation, but they are they are not nonlinear. There is no nonlinear term here. You see, I di dt equal to minus gamma I, dr dt equal to gamma I. There is no interaction between, means there is no such term that is I into r, gamma into I into r, means degree of second degree. There is no such kind of relation here. So these are nonlinear coupled, these are linear coupled equation, not nonlinear. The complexity come when there is any nonlinear term is introduced in the model. That will happen, means we will see later that nonlinear term would be there. So then you can solve the nonlinear equation by analytically. That is not easy to solve. Only few nonlinear equations could be solvable analytically, but most of them are not when the model become more complex. So then you will use numerical, we will use the numerical approach, numerical method. Numerical approach means you have to solve by writing a code. We will use some algorithm, any kinds of, there are different kinds of algorithm, but we are not going to describe different types of algorithm in this class. You can for MATLAB, you can use some solver, ODE solver or different ODE solver in R, MATLAB or Python or anywhere you'll be getting. You can use those solver and you can do this. I'm not going to teach you that what kind of algorithm behind these numerical simulations, but you can use anyone, whatever you prefer. And the analytical approach. So let's start to solve this problem by analytic approach, because this is solvable. We can solve it easily. So our model system is di dt equal to minus gamma I and dr dt equal to gamma I. So is it really two equations, two sets of equations? What do you think? Means can we not solve only one equation and I can get the result for the other one? Means say if I can solve, means if as the total population is constant in the system, these completely closed systems I and R, no one is dying. So we can think that I plus R equal to constant, right? That means this actually converts to a single equation. We can easily convert these to a single equation. No need to do, means there is no meaning of these two differential equations. So if we can solve di dt equal to minus gamma I, then automatically the other equations could be solved, because I know I plus R equal to 1000 here. That is known. So what will be the solution for this equation? So di dt equal to minus gamma I. Anyone can answer this?
I equal to I0 into e power minus gamma t.
Yes, correct. Exactly that. So this is very simple equation. So you know that this will be exponentially decaying function. I equal to I0. If you analytically the way we learned it in the lower grade. So di by I equal to minus gamma t. Then integrate in both sides, and you will get the solution I equal to I0. Means some constant e to the power minus gamma t. Now, if you solve I0, what is I0 here? I0 means at time t equal to 0, what is the initial number at that compartment at I? So that is I0. That means I equal to I0 e to the power minus gamma t, where I0 is the initial value of I. Okay. So now, if we know that I0 equal to 1000 as per this problem, and we have to find out, the question was what what proportion would be in the I compartment or in the recovered compartment after 28 days. So you can easily get this number, you can easily get the answer by putting I0 equal to 1000 e to the minus gamma t, gamma equal to 0.1 per day, and t is 28 days. So after that, these many people should be in the I compartment at time t. So if you put this value, and the I would be, you can see this, that I would be 61 infected people. after 21 days. Initially, there were 1,000 people in that box. After 28 days, after 4 weeks of time, the number of infected people in that box would be 61. And so the remaining would be in the recovered compartment. Where they are going? They are from I to R. So remaining 939 people, in that infected people will be transferred to the recovered compartment or immune compartment. So this is around, according to question, you have to have the answer that around 94% of the total populations are in the recovered compartment, in the recovered box after 28 days. Mostly 94% are recovered after 48 days, 28 days. Clear? So this way we can plot. Now the next question was, you plot these scenarios, means after 28 days, what will be the population size in different groups. So we can easily plot it by evaluating the value of I and R by putting a value, a particular value of t, means at t equal to 28 days. I just, we have estimated that I would be 61 and R would be 939. Now at 27 days, you can find this value. At 26 days, or from starting from 0 day to 28 days, you can individually find out all these values, I and R values. If you plot them together, then the curve looks like this. So here the red line represents the infected population. They are gradually decreasing, they are recovering. So R is going, means say exponentially decaying curve. So it is coming down from 1,000 to up to 21 days. It is reaching to, at this point, what we have seen in the last slide, this is 61. And the recovered class or recovered people, they are gradually increasing because these are coming to the other group, means red are going to the green group, we can say. So recovered people are gradually increasing, and after a certain time, it is reaching to the maximum level here. It is up 20 days, it is reaching to here. So if you continue this, means say we have simulated this for 28 days. If we can simulate this for 100 days as well, so then we can see when the disease will be completely eradicated. At what t value, at how many days it takes to eradicate the disease at that in these conditions. We can find out this. There is one question here that in when the infected and recovered population would be the same, it's 50-50. So this is the point. The infected and recovered population would be the same, right? You have that data table that in what many days, what is the value of I and R. You can easily see this. You can find it that this is the time when the infected and recovered population would be in the same in number. Then if there is one question that when it will be the disease will be eradicated from that cohort. So you can easily find out when this would be going to the zero. Not zero, not exactly zero, but if it is less than 0.5, we will consider that it is zero. So fractional 0.5 population, it is meaningless. So we will assume that that is a zero value, and by that time we will be reaching to the disease will be eradicated from that cohort. It is around 7 days it will take. Now then I asked, means in the same question set it was there that now varying gamma, try to understand how gamma behaves in the model. Varying gamma, how it affects the output of the system. If infectious period is 2 days, recovery period would be 1/2 days, as we learned before. So if infectious period is 2 days, that means recovery rate gamma would be 1/2, means 1/2 means 0.5 per day. Similarly, if infectious period is 20 days, the recovery rate would be 1/20, that means 0.05 per day. Now you can simulate this scenario by yourself, right? The way the method we learned now. And we are solving this till now, we are solving these things analytically. So now, with recovery period, infectious period equal to 2 days, that means they are staying in the R, average duration of staying in the same box, in the I box, is 2 days. That means they are rapidly moving from I box to R box, means recovery rate is higher there, right? If recovery rate is higher, that means people will be rapidly recovered, rapidly from red line, the shifting from red line to green line will be more rapid when the infectious period is less. If infectious period is longer, say 20 days, then that means it will take time to move from red box, means red line to green line. So that is happening here in this figure. You see here in the first left hand panel figure, it shows that red box is gradually decreasing over time, slowly decreasing. The opposite. It is rapidly decreasing over time, and simultaneously the green is also increasing very rapidly. But here the process is slow. If infectious period is 20 days, that the process is slow. That means a long time they are staying in the same box, in the I box, then they are gradually going to that green line. So the time when the 50% would be recovered, and the question that I discussed in the last slide, when 50% would be recovered and 50% would be infected. Here you see within maybe 1.5 days, I think this one is, as I noticed, 1.5 to 2 days, it will be reaching to the 50% would be recovered within 2 days. But here it will take around 2 weeks time to reach, 2 weeks to 15 days time to reach this point, means 50% recovered and rest are still infected. Still now, do you have any question from here? Hello? Can you hear me?
Yes, sir, we can hear you.
Okay, okay. So is everything clear still now?
Yes.
Or if anyone has any doubt, because I will be going to there is only one slide, then I will give you some assignment to do just now. That's why I'm asking. If you have any doubts till now, you can tell me now at this stage. Okay, so everything is clear. It's very simple thing. So let's go to the next slide. So this is actually the same thing I plotted for two different scenarios together.
Sir, your screen is not being shared.
Oh, it is not. Yes. Let me share it again then. Can you see now?
No, sir.
Not yet?
Not yet.
This is the problem in online setting. Share entire screen. Just let me know whenever you can see my screen. Strange. Can you see now?
No,
Can you
sir.
see my? No? It should come.
Not yet.
What is happening then? Okay, so let me share my tray only. Only Windows. Now?
No, sir. So maybe you can leave and rejoin and then share the screen again.
Yeah, that will be better, I think. Let me do that. Now let me try again once more. Can you see my screen now?
Yes, sir.
Yes, sir. Now
Okay. Okay, great. Showed you in the earlier slide. Now we'll be doing together, plotting together actually. If gamma equal to if gamma corresponding to 2 days of infectious period and gamma corresponding to 20 days of infectious period. In the same plot, when I am plotting these things together, you can visually see these things, the changes actually. So that is the reason we plot it together. Nothing else. Means the previous slide and this slide is same actually. Hello. I I I think it disappeared again, right?
Yes, sir.
So let me connect in another machine. And there is some problem in this. Some code is running. Maybe that is the reason. Let me just give me 5 minutes time.
Sure, sir.
So I'm connecting in the next machine.
Am I the only one who can't hear anything?
So we'll rejoin in 5 minutes.
Oh, okay.
Hi. Yes, thank you for connecting me, and sorry for the for the disconnection. I just changed my machine. I'm starting from another machine. So I'm audible, right?
Yes, you are audible, sir.
Okay. Now let me try again to share my document slides. And share full screen. That will be better. So you can see my screen. Can you see my screen?
Yes.
Yes, sir.
Okay. Okay. We're here, right? So the main thing is that feelings of different parameter and how it relates with the model. Means that feelings should be there. Means you should have that feelings. Okay, this is this is possible. This is not that something absurd. So if recovery rate increases, that means the people will be recovering rapidly, and they will be reaching to the immune compartment faster than the if recovery rate is slower. So these things are coming out from here. So always, whenever some model projects something, you have to relate that way from your with your common sense. That yes, this is projecting properly. It's not if something happened the opposite way, then there must be something wrong with this. Otherwise, model will not give you something absurd. Means that you have to correlate always. So all this goes as I said, that analytical approach. These up to this you can solve all these things in analytically. But the second approach that is important, and we'll proceed with that approach only on the next slides onward. That is numerical approach. We'll not try to do these things analytically. Some solution, some problem could be solved analytically, but most of them are not. So and we will gradually shift it to from analytical to numerical solution to solve that. So I will show you one example of numerical solution of this problem in R, in R language. You can write it in any language, though I told you. So by those I think few of you are familiar with R platform. So you have to provide that library function, this dsolve, and then graphics to plot. So you have to give these inputs, and you are defining now the initial conditions for this problem. You have initial number of infected people, 1000. Initial number recovered. Initially they were 0. Then you have to assign the recovery rate and follow-up duration. Means how long I will want to simulate, how long I want to see these results. Then you have to it writes as a structure way. You can write it as a initialization means I. You are renaming this is I and R. I means initial number of infected and R is initial number recovered. Then parameters as a string. Then how many times you'll be solving the sequence, and finally that model you have written with this function. This function actually this is the solver. You will solve this one is the solver actually. Then ODE solver. By using ODE solver, you can get the output. So you might be familiar with this technique. I'm not going in detail step by step for this methodology. This is just simple numerical method. If anyone needs any help on coding or solving, you can separately mail to me, or you can consult with Sardul or Sagar. They are assisting in this class. For this class, they are along with you, so they can help you solving this code. Means either in any languages, means whatever I think they are comfortable with Python, so they can show you how to solve this if someone is not familiar with any programming language. So this basic language to solve ODE equations. Just that knowledge is sufficient for doing this exercise. Now, this is the output from that R coding. If you see how the population will grow and how it will change over time, you can see this. This is the output. First column shows the time, then infected population, recovered populations, and corresponding the plot. Here you can from earlier figure actually we mentioned that at this time point at day 7, the recovered compartment and infected population would be 50%, 50 and half at this point. So you can see here actually at day 7, see the nearest point is at day 7, 496.6, about 497, and this 503, right? So in day 8, 449 and 550 means closer point is that 7th, day 7th. Means it would be between 7 to 8. If we the time step in fraction, you will get the exact number. But as it is in the day, so it would be between 7 and 8. But this 7 is the closest day when both the population would be same. So it gradually, you see that this one is gradually decreasing, and this one is gradually increasing somewhere. The figure what is depicted here, the same thing. Now the next step of the problem. Now you are supposed to solve this problem. Just now I will give for of course briefly I will describe the initial step. Then you will try by yourself to solve this problem. Okay, just now, and I want to see how many of you can give the answers, correct answers. So the problem is now earlier you have infected population and recovered populations. There was no disease-induced death. No one was dying from the disease. Now, just introduce one sort of complexity by introducing disease-induced mortality in the model. Now we want to solve this. The question is what to means you have to introduce first disease-induced mortality. How the model diagram would look like with the mortality, how it will change the figures and diagrams. I will explain up to that. The next question onwards, that means after 4 weeks time, what we expect and other things, and the remaining questions that you will do, and accordingly means as per your response, I will be going to my slides. Okay. So for the first step, how will model that mortality rate? Here I will introduce that thing, that terminology, mortality rate. Here I am depicting this as mu, that mortality rate. Is it correct way of presenting it here that I to R, you know, I to R with the arrow and the rate gamma. This is fine. Now people are dying from the infected box, not from the recovered, not from the recovered compartment, right? So is it correct to present it means before recovering people are dying? So if I put mu in the R box, is it correct way to do? Or there is something wrong?
I think
So
it is
they
not
might
correct.
die.
Sorry, tell me. Is it just repeat it?
So they might die before recovering.
So that means they actually normally what happens means people die during infection, not after recovering from the disease. For some diseases it occurred, but no, that is not normal. So long term impact, if you see that after 2 years from recovering some disease, people can die. So that is the reason is different. But usually what happens, the people are dying means for some disease means they are dying from the eye box only, from eye compartment, right? So this is not the correct way of writing things. So this is wrong. This approach is wrong. Now, what about this one? What do you think about this? Can I write this way? I to R and people are dying. So is this correct way? What do you think?
Sir, here also it is similar to the last case, right? That only that fraction gamma of people that are moving towards recovery, we're saying out of that a fraction mu will die. But I might have understood it wrong, but I thought that from the I box itself, mu fraction might move out before recovery.
So that means according to you, who are you? Can you please tell your name?
Sir Himank.
Himang. Anyone else?
Sir, I also agree with what Himang said.
So this is not correct then. I think that this could be correct. Why not? I don't really understand this. Can anyone tell me any other reason?
Sir, it might just be that we're interpreting it differently. I think the way we are interpreting it is that out of gamma, a mu fraction will die. But maybe what you mean by the diagram is that mu fraction from I will die.
Yes, means if I present this in terms of fraction, there are two things you should remember from the beginning, from constructing all this kind of model. Two things actually in last class, if you remember the last class, then I told about I described about rate and proportion. If I write, means you must have this kind of transition must have some rate parameter. If we depict that mu is not rate, mu is some proportion, and gamma is also some proportion, and it could be in another rate, means maybe from I towards some other rate, say alpha. Alpha is the rate, and gamma proportion is recovering, and mu proportion is dying. That is true. That could possible. If I give some kind of statement before developing this model, means if I say that I people from the I box, people are moving to R box at a rate of alpha per day, and among them gamma proportion, I'm saying that proportion, not rate now, though that is not correct. If I say that gamma proportion is going to R compartment and mu proportion is going to the for their dying among them, then this could be okay, fine. But unless that, as I said, that gamma is a rate and mu is also a rate, you can try it this way. This is not correct. Everyone who have answered, their answer is correct. This is not the correct diagram. So correct diagram should be something like this. Right? The people are dying at a rate mu from the I compartment, I box. So arrow should be from the I box and recovery rate from I to R. Clear? Now for the next step, the questions. Now you have to answer actually. What was that question? Modeling an infected code. So these understand, you understood this, right? That mu should be in the I box, not from at the middle of I and R, nor not from the R. It would be going out from I. Now the set of equations are for this model would be, first part would be similar, di dt equal to minus gamma I. From I, the number of people moving out from I is minus gamma I. Also, people are dying from this box, so we have to remove that term from I, right? I is changing because of their recovery and because of their dying. Both together, they are contributing for decrease of I compartment or the people in the I box. That means di dt equal to minus gamma I minus mu I. Is it okay? So we can write the differential equation for I equal to di dt equal to minus gamma I minus mu I. But for R box, the number is only entering. There is no depth from the R compartment. So dr dt equal to gamma into I. This is entering in this box. And we can count how many are dying from the model itself. If when we will simulate this model, just now we'll be doing these things in your code, in the programming language. So how many are dying? If you want to count simultaneously, then you can write an equation for death also. Means I have not depicted any another box here. I could put one box here by saying that this is M, means mortality. How many are coming here after death? So that equation for that box could be dm dt equal to mu into I. Those are going from I to that box, right? Now solve these questions by your own. Then I will check whether my result is correct or I did some mistake. So now at the beginning, you suppose their number of population is, I think I considered here was 1, 2, 3, 4, 5, 6, 1 million people. 1 million people infected, 10 lakhs people infected at a certain time point. Okay, that could possible in India. So 1 million people are infected. So they are in the I box. No one has recovered or died yet at the beginning, means at t equal to 0. Then their recovery rate is 0.1 per day, means 10 day per recovery duration is 10 day average duration. And mortality rate is given here, that 0.2 per day. Now we want to get some information after 4 weeks time, what would happen to I and R. It would not be the same as we can expect that the result would be same as before without mu. Earlier result we solved it without mu, but now introducing mu, the result would not be same. So after 4 weeks time, earlier we have noticed that around 94% were recovered after 4 weeks. But if we have mortality, if we have death among the infected group, then how many people will be recovering after that? Can you please try this? I can start time now. Or if you have any documents at this stage, if you think that now it will be difficult for you, then I will move, I will proceed. So, but I would suggest that you please try it. And now it is about 3:10. I'll give you 5 to 6 minutes, 5 minutes time. I'm expecting this to be done. Because you will be using a solver anyway. So I will come back again in 3:15. Hi, Sagar. Yeah, actually, I'm trying to connect from another machine together. Means in one machine where I'm presenting in the presentation mode, I can see any other. So I'm connecting in another name. I'm trying to connect it in from another machine. Can you please allow me to join? Yeah, I'm asking you, can you please allow me to join in that machine? In the same meeting, I'm sending, I'm joined in a single machine, single laptop, right? So I'm trying to connect in another machine to see all students together. Means because when I'm in presentation mode, I can see anyone. So I opened the second machine. Please allow me to accept me to join. Okay, please do that. So what is the status? Any progress? Anyone has any progress, or shall I go to the next step? Shall I show you now for the time being?
So you can go ahead.
Okay, so did you try or not try?
Yes, sir, right.
Okay, there is any problem, there is some problem on simulating. All right, so it would be, is it fine if I shared you some codes, some basic codes like this? It would be helpful for you. Then I can share you that after this lecture, I can share you some basic codes. If you are not much familiar with this kind of by solving this kind of equations, then I can share you some basic codes. At least means I can share you in R, or I can share some codes in MATLAB. That two versions I have, but I don't have anything. Means I don't know Python. So if you ask me to do in Python, sorry, I will not be able. But you can get the feelings how to solve it in any language is similar. So I can, after this class, actually, I could share you in code in R and in MATLAB. So I'm going to the next result, next step of the result, how it will look like now. But later on, you please do it. Okay, so let's see. At least you can tell me. You can answer me without doing anything, without doing any simulation or analytic solutions. You can answer these questions. After 4 weeks, do you expect more people to have recovered or more people to have died? And why?
We would expect more people to die because the mortality rate is just twice of recovery rate.
Yes. So from that rate parameter itself, we can get these feelings. Right. So easily we can say that. But the if the question is something different way, suppose recovery rate is 0.1 and mortality rate, instead of giving mortality rate, if I say that 40% people die from that infected compartment in 2 weeks time. So then the answer would not be so easy, right? Here, as the both gamma and mu are in rate, are given in terms of rate, then it is easy to answer that yes, people will be dying more than they're recovering by this time, because mortality rate is higher than recovery rate. You can tell it easily. But if the information is something like this, that recovery rate is 0.1, that means from the field data. Yes. From the field. From the field data, actually, you will be getting the information from how many days people are recovering from the disease. Means in 10 days,
Sir,
in
could
10
you
days people are
please-
recovering from disease, so recovery rate is
Sir, could you
recovery
please
rate is 0.1.
mute one of the mics?
Yes, I did that. I
Okay.
felt that there is some problem echoing. So I switched off that one. So if recovery rate is 10 days, then from there means the kind of information we get from the data itself is not no one will tell you that gamma equal to 0.1 per day or mu equal to 0.2 per day. But the information you get from the field or real life data is that recovery rate is about 10 days people say recovered from infected compartments, means recovered. Means duration of recovery, average duration of recovery is 10 days. And you will get to know that death rate, instead of death rate 0.2, you will get to know that at least 10% people are dying from this disease by 2 weeks time. This kind of information you will be getting. So these informations, these type of informations has to be means for your modeling purpose, you need to translate this in terms of rate, right? So as mu and gamma both are given in terms of rate, it was easier to answer the question. Yes, as mortality rate is higher, mu the rate is higher, so people will be dying more than recovering. Instead of, means I am saying that instead of giving these informations, if you are given gamma say 0.1 per day, that's fine. But instead of mu equal to 0.2, if I say 50% are dying during that period, so then now then compare. I think after this discussion, you would be able to answer that question as well, right? You can translate. If I say that for 50% a day, then you can translate that from the competing hazard, from the concept of competing hazard. What 50% dying means, what is the value of mu? Already you learned mu by mu plus gamma, that is called competing hazard. Mu by mu plus gamma equal to 0.5. Right. So you can estimate the value of mu, and you can easily compare then mu and gamma. That is the way of estimating that mu and the parameter, and you can conclude from that. So all right. Now numerical simulation, as what I have asked you to do is that to get these results from your by using your machine by writing a code, simple code of I versus R and M. Here there are two columns you see, and these are the outcome of the simulation. Time step from 0 to 28 days, and then how I is changing. 1 million population means 10 lakh population initially, and then R and M. M means the deaths. There, see, earlier in earlier example, I remembered around 94% were recovered at the 28 days. Now you can compare how many are recovered from these data set, from the lowest row. You can see at 28 days, around 225 people will be in the infected compartment, 33 lakhs people in the recovered compartment, and 6 lakhs are dying, death. Means people are dying more than recovered. So almost double, because the recovery death rate was double. Right. So that things are coming out from the simulation itself. Means what you have suggested before doing this simulation, that is completely matching with this number. So based on the model assumption, what proportion of the initially infected cohort died before recovering over 4-week period? So from this information, you can easily tell the result. That would be around 66%, 67%. So if you divide that, how many are recovering before died, means 33 lakhs divided by 10 lakhs population, that would be around 66% or 67%. The next question was, now use the competing hazard formula in the last lecture what we described. So to check the result, whether this is expected or not, after 20 or 8 days means almost the epidemic is over. Then how many people will be dying means from the death proportion of death, you can calculate from here itself. So how to do that? Means you have to find out case fatality rate. Case fatality rate equal to mu of mu plus that from that formula directly you can estimate this value. It would be 66%, means 0.666. So it is same simulation, numerical simulation. What we have seen that sorry, earlier I missed it. This is not recovered component. This is actually death. Death would be 66%. So here from analytical calculation or from the concept of case fatality rate also you can find the same number. So this would be same. So numerical results and analytical result means from the concept of case fatality rate, both will give you the same number. You can check this or verify these things. Now this is very, I should not actually give the answers. It is already, I'm projecting the answers. Otherwise it will take time for you. Otherwise you can easily solve this. If the question is something like this, if the case fatality is 50%, assuming gamma is fixed means 0.1 per day, then calculate the value means of what would be the value of mu from this measure, means if case fatality is 50%. I think you can means 50% people will die at the end of epidemic. For what value of mu? So the formula is same. Case fatality rate equal to mu by mu plus gamma. Now here you just rearranging all these things to find the value of mu, and ultimately you know the value of gamma and case fatality rate, both are known. So what is the value of mu? So mu equal to 0.1. From this, if you estimate this, mu will be 0.1. Is it clear? So this clear right now, right?
This is clear.
Okay. So means you see now the rate and proportion and percentage. What percentage? If this understanding is clear, then there will be no issues on developing any kind of model. Means people usually do their mistake in formulating this rate, translating rate into proportion or what value we'll be using. These are the common mistakes that happen normally for developing models. So if this is clear, then okay. Now, as of now, what we have developed, these are called cohort model. The example I showed you for 2 examples from practical session 1 and 2. Those are called cohort model because we are only dealing with some cohort of populations, infected cohort and recovered cohort. We are looking at that, this number. Now for the disease transmission, this is not the, I'm not really, I can say that this is disease modeling, transmission modeling, because I am not showing any other component. How the disease is propagating is not captured by this model. It's only one cohort we are looking at. Now we want to see how disease is propagating. So disease is propagating means there will be some uninfected people at the beginning, means those we can say that susceptible population or uninfected population. Now they will be gradually translating to infected and then finally recovered, right? So for the next 2 days, already you have learned how to model from I to R compartment using that rate gamma, and even we have introduced mortality rate later on. So the set of equations, governing equations, is di dt equal to minus gamma I or dr dt equal to gamma I. Now for disease modeling, we have to have some susceptible population, means those are not infected yet, those are susceptible to the disease, or uninfected populations. They should keep in a single box. Now we have 3 categories of population. One, those are not infected yet, those are uninfected or susceptible. Then the next step, people after getting infection, means either from bacteria or virus or any kind of infection, if they get that infection, they will reach, we'll keep them in a single box, I box or infected box. Then if they recover from there, we'll send them to the R compartment or R box. So next two steps is known, already we described a lot. The first step is the susceptible to infected compartment. Now I have introduced another parameter. So as a rate parameter, as I said that for any transition we have to introduce some rate parameter. Here from susceptible to infected, we have introduced a rate parameter lambda. Greek letter lambda. Usually means you can use any other symbol, but this is a standard symbol. For recovery rate we use gamma, and for infection this is called force of infection. Infection rate we use lambda. This is standard formula. So don't try to use any other language. This is very standard. Everyone use this. So try to use the same parameter everywhere whenever we will write some equations. But if you write so instead of lambda, if you write alpha, that is not wrong at all. But this is the standard terminology. So susceptible to infected, then infected to recovered. Now we have to now we have three variables. Three box means three variables. The model is becoming complex now. From I to R, that was fine. Now we have to write another equation for S compartment. What should be the equation? Can anyone tell me? If lambda is
ds
the
by
rate,
dt.
yes,
ds by dt equal to minus lambda s.
correct. ds by dt equal to minus lambda into s, as exactly similar to the I means to the equations that written for I box. But now ds by dt equal to minus lambda s. That means people are moving from the S box, right? Where they are going right now? After leaving the S compartment or S box, where they are going now? They are moving to the I box. So the now, I think, what do you think? Do you not think that equations for I has to be changed now? That is not correct. The current version is not correct anymore for I.
Yes, I
So,
think a lambda s term should be added.
yes, the people who are leaving that S box, they are entering the I box. So that number should be added to the I box now. So ds dt equal to minus lambda into S. Similarly, di dt has to be revised, not minus gamma I, but lambda s minus gamma I. Right. So now these people are entering in the I box. So lambda s minus gamma I. And dr dt is the same. There is no change in the R compartment. Only change is in this box, in this flow actually. Right. So this is the first step of infectious disease modeling. But still there is something I'll come later. So this called here we are assuming that lambda is a constant rate, as we assume gamma is a constant rate. This is the assumption. Gamma we considered as a 10 day per second, whatever the value, but gamma is a rate which is constant over time. Now the assumptions for this model is lambda is also another rate at which rate susceptible population is getting infected, transferring to that infected box, infected compartment. So lambda is constant, gamma is constant. Now you can do the similar experiment what you did before for I and R compartment. Initially, I thought you'll be doing in this classroom, but I think that would be difficult for now at this moment. So if you, at least if you write one code after this class, if you have some sorts of code for these sets of equations, SIR model or IR model, some code 1, code 2, if you write those codes and then you can easily changing the equations and variables. You can easily replicate that code for another problem also. So in the next time, I would expect that you'll have these codes in your machine so that you can, it will not take time for replicating or replacing some variables, some parameters to see the other results. Okay. So I'm going through the results as rapidly as possible. So these are the set of equations now. What are some example actually? example situation for COVID-19 virus epidemic in China 2020. At the beginning, there is no one, coronavirus had not, that time it was named known as coronavirus, had not spread there before. So everybody was susceptible. Before going to infection, everyone is susceptible. So initially say, I think 3, 4, 5, 6 means 10 million. Initially 10 million were susceptible. Only one means 9,999 million, but only one is infected. So because the virus is new, everybody is susceptible to that virus. So at the initial stage, we can say infection means we have introduced I equal to 1, and the remaining population is in the susceptible group. Now for a given lambda, if we know that transmission rate is this, you can easily tell from by simulating the problem, the equations, model set of equations, you can easily tell me that after 30 days, what will be the how the epidemic will look like. Means how I will be, how big the I would be. What are the projections you might be knowing that you might remember those things, that the kind of projections are coming out, that people are saying that no, the today the number of cases is this many, so we are expecting the number of cases would be this much. Actually, from these kind of sets of equations, you can project these numbers easily. But of course, for reality, the system is not so simple. So as much as you can capture the reality in a wise way, you will get closer to that closer prediction or projection of the real results. So now again, I thought you will be doing this here, that considering that force of infection is lambda, constant force of infection 0.2 per day. If the rate of lambda is 0.2 per day and infection has an average duration of 10 days, then you do this solution. Means try to solve this equation. Again, after 2 months period, look after see the plot after 2 months period, what is happening. What does this how does the number of people in the susceptible and infected recovered compartment changes over time? That is the first objective. Means you plot these 3 variables together and look what is happening. Means try to understand, relate with your common sense and with the model and model equations. You always have to be try to relate these things. This is important here in epidemic modeling. After how many days the epidemic reaches to its peak, and what does it when does it end? These are the questions. You can just, I'm showing you the plot, but try. I will expect that next time in my next class, by maybe after 1 week, not next week, after 1 week, after gap of 1 week, I think next week Professor Kulkarni will be taking the class. So you'll be able to solve this. You'll plot by yourself. So here see, infected population is actually growing here, the blue line curve. If we initiate in a single infected population, now it is increasing, then it will it reaches to at a certain level peak, then it gradually decreases. Simultaneously, susceptible population is gradually decreasing and recovered. As everybody is recovering, there is no death in this model. We have not considered any death. So recovered compartment is gradually increasing and it reaches to certain value. Means if this is 0, then this would be maximum. Actually, what is happening at any point, if you don't consider mortality in the model, then if at any time point, if you add up all these 3 variables, you will see the total population would be the constant, that what is the population number, population size, that will match with that. This is actually cross-checking of modeling result. Sometimes we need to check whether what the simulation is giving me, whether that is correct or not. If you say at time t equal to 10 days, if you add up this value, it's susceptible plus this one at this point, what is the value of recovered number plus this number. If you add up all these, then you will get 10 into 10 to the 5 means 10 to the 6, and so 1 million probably. That would be remains constant over the time, as there is no death on the model in this model current version. And you can see that the pattern of I, it is going up and down. You remember, and during my first talk, actually, I showed you some result from Ross's analysis, Ronald Ross model. And before that, actually, there are some kind of analysis from data analysis. Means they see the pattern. They observed that how number of cases increasing over time and then gradually decreasing, but they can't explain why it is happening. Means they can explain that yes, this is happening. We have observed that in some diseases, in pox, in many other diseases, the people of infected people has initially increases and then gradually started declining. But they can't explain the reason. Especially, I gave the example of FAR for some epidemic. I think polio epidemic, as I remember. So it increases and decreases. They noticed in twice, but they can't explain the reason. But here, from this modeling concept, from this the conceptual model, it gives you why the curve is going up and down. So you can see all these curves, how recovery is happening, how these things are happening, and this matches on the reality. Means we have seen that this goes up and comes down. Is matching with this number. Okay. So we'll go to the next step. Just some biological terminology, I can say. Might be some of you are familiar from last lecture of Professor Kollani. But let me go through this again. No need to. Actually, I am not going to explain all these steps or whatever written here in details. But the thing what is needed is the concept of SEIR. Here it is written in some boxes. It is written S, E, in this box I, in this box it is written as R. Actually, this is the epidemiological compartment. And now, still now, we learned about susceptible population, infected population, recovered population. We can divide those kind of the full population into several categories according to their disease stages. So this very general concept, of course, means very for disease modeling, we use this terminology very frequently. It's SEIR. What does it mean? S means there is no virus or there is no pathogen in that those people. In S compartment, there is no pathogen is not introduced there at all, and they are susceptible population. So we keep them in S. E means when they get the infection, means someone has COVID. That does not mean they started, means after getting COVID, they started spreading COVID. That is not true. It takes some time to develop, to rapture the to develop the virus or bacteria or any pathogen within our body. Then they become able to spread the disease further to the next person. So once the disease is introduced in this box, means in the E box, the people are here, they are not infectious at all. They can spread the disease, but if you test them properly, you can detect, you can identify the virus or bacteria or pathogen in their body. In the next group, in the I box, the meaning of this box is means virus is there and virus load is virus or bacteria, means whatever the pathogen is, that is load is much higher than in the E box and in the developed states, so that they can spread the disease now. They are able to spreading the disease now in the I box. So people are here are infectious. We say them are infectious. E are not infectious, but I are infectious. Now, after recovering from the disease, they can transmit, means the virus has been removed, virus or those pathogens has been removed from this group, but they might have some immunity. They have developed some immunity against the virus in their body. So if you test them, you will not get any virus, but you can say some T cell immunity or kind of immunity they have developed for this group, for this R group. Okay, so these are the structure. Means here in the blue bar that there is a gradient of color gradient. You can see that actually this represents when there is no virus. As blue is increasing, means the virus load is maximum, at this stage at I group, the virus load is maximum, then gradually is decaying. Okay, this happens in reality. Now we'll be using other terminology also, latent period. This E box, when the pathogen is getting developed in this body, within this body, the people say within this body, or so we say them, this period is latent period. They are not infectious during this period. There is another terminology, it's called, just remember this terminology. It is not for modeling purpose, we need to, we'll be using this term frequently. So just try to remember that what is the meaning of latent period or latent infection. We can say that this is latent infection. Sometimes we'll say latent infection. We can say they are exposed class. E actually signify that exposed. Exposed means they have the virus, they have exposed with the virus, but they are not infectious yet. So latent compartment or exposed compartment, we usually written as E. And other terms like incubation period or symptomatic period means you can divide this E and I in two categories again, incubation and symptomatic. Incubation period means after latency, there is a chance of, at the last stage of latent period, actually, there is chance of they have not developed symptom yet, but they can spread the disease. Maybe the infectiousness is lesser than on the people who are in the symptomatic class, but they can infect. And during this period, this is called incubation period, when they have not developed symptom. And according to when they develop symptom, they are here, and the other way. I'm not going to explain the status, these things, PCR and other terminology. ACIR, what is the meaning of those? Though already I explained what is needed for your purpose. These are not required for now. Now again, if you can solve this problem just now, because you don't have to do these things in computer simulations, I am not giving any computer simulation problem. Then I'll be happy, actually, means then I'll be then I'll confirm that you learned the subject whatever we teach still now. Construct a TB model, very simple TB model, this one, and indicate the rate parameters as given as per the given information. TB is a disease, bacterial disease. It moves from, say, uninfected class. There are some uninfected class. Then there is some latency class. That's why I introduced a slide there before this section, before this slide. Latent TB means they have the infection, but they are not spreading the disease. Now the next step, they develop active TB. They can spread the disease. They are infectious, and then they finally get recovered. The informations are given something like this. Average infectious period is 3 years. Case fatality rate is 50%. Latent TB, 10% lifetime risk of getting active TB. This is the information given in the latent TB compartment. They have a 10% lifetime risk of getting active TB infection. Means 10% of them during their lifetime, 10% of them can develop active TB. Okay, the meaning of this. And also it is given that average lifetime without TB means people are dying, people can born. So if there is no TB, I'm not saying about TB induced death, but natural death. If I don't have TB on the whole life, I obviously I will die. The average duration or longevity of human life in India is around 70 years. So average lifetime without TB is 70 years. Now, take your pen and paper and try to populate the numbers. What could be the rate parameters, and put the arrows over here.
Sir, in the previous slide, could you please explain how to go from uninfected to latent TB again, like with this?
Okay. So
this data.
So just to understand latent TB, right? That is your intention to understand.
Yes, I understood latent TB, like this is TB that someone has, but they might not know. But I didn't understand what is the metric we use to go from non-infectious to latent.
Non-infectious to non-infectious
like uninfected.
to latent? uninfected to
latent.
uninfected to latent. They have the disease has been introduced here. I mean, say suicidal people. So for malaria, suppose for malaria, I don't have in malaria at this stage. I don't have malaria, but now one infected mosquito bites me and inoculate the plasmodium, either falciparum or vivax, anything, to my blood. Now I will go directly to this E box, E compartment. But that means that already the pathogen is within my body. But at this stage, I cannot spread the disease to any mosquito, because to develop the pathogen within our body for specifically for malaria, I can say that takes around 20 days, 20 to 21 days. That bacteria, that pathogen will develop within our body, that parasite actually developed that goes directly to liver, and there it develops and with spore, they produce sporozoite and they rapture it in the blood cell. Then it comes to the blood, and for the full process it takes around 20 days or 21 days. So that period is called latent period, and in that person is in the exposed compartment or E compartment, E box. Is it clear now? Now,
Yes, sir.
once
Sir,
the
I
parasite
understood the-
is in the blood, now the another mosquito, if bites after that, then it can infect another mosquito. Yes, you have another other questions, I think. Just tell me.
Yes, sir, I understood what latent period was, but how can we measure latent period?
It is very difficult. It is very difficult. You can directly measure this. Means it's not by looking at them or by just without doing anything. It is very difficult to measure the latent. But you know, means you can do experimentally. Of course, you can come to know. But by looking at them, it is difficult to identify that these are in the latent. Especially for TB, it is very difficult. For some diseases, it is you can come to know, because we know now after dose. Actually, we know how parasite develops within human body, how it from once the parasite goes into our blood, and then how it develops through in the liver cell and how it comes again in the blood. For this full process, you can test in each step. You can test the blood and you can check what is the parasite load in blood, and you can check the latency period. You can estimate that. But the process is not so easy. But just by looking them, you can tell that this is he is in the latent period or latent infection. And it is more difficult for the disease like TB. For TB, actually, you know that around 30 to 40% people in India are with latent TB. I might have TB, but I don't know it. And lifelong, I will not be knowing that I am latently infected TB patient. The disease will be suppressed within our body, but it will not develop any symptom, or I will not be able to spread at all. That is also true, but the disease is there. And around 40%, 30 to 40% population in India are with latent TB in this compartment, in this E box. This you can imagine, means if everybody develop the disease, then it would be a huge number. 30% population means 1.4 billion population in India. Then 30% having TB means how many population having TB? You can you imagine? So but it's okay. Means it is not we need not to be so much concerned about them, because they are not spreading the disease at all. But they can have this.
Got it,
Is
sir.
it clear? Okay. Now come to this. Now here the latent TB means the people are having this the disease within them, in their body, but they are not spreading the disease. Now the information I got it from epidemiologists or from doctors. They give these kind of information. Average infectious period for TB is 3 years. Case fatality rate is 50%. Means people are dying. 50% people are dying if untreated. So now this is the very simplest model, and we are thinking there is no treatment, nothing is happening. All just prehistoric era. We are there, so people are dying with TB. So and this is the assumption that 10% means in the latent group, though latent group populations could be much higher, but only 10% of them are going to the eye compartment. 10% of lifetime risk of getting active TB from the latent group. And average lifetime for all this compartment is 70 years. Now, how can we write this in structure from model structure? Just build the model structure and give some any arbitrary parameter name and put these parameter values from these information, whatever available here. All parameters are not given. So you can, but from these informations, what could be the parameter value? Or you just take 5 minutes time and tell me one after one. Means I will ask one question, first questions where to put and how to solve. I can give you 5 minutes if you need, or if you don't need, then we can discuss right now.
Sir, one question.
Yes.
Do we know how many people are developing a latent TB, or we don't know anything
No,
about it?
and, from this information, we don't know anything. From this model structure, what was the information given here? Here we don't know how many are developing latent TB. So for that, actually, you don't have to put any parameter value. Just indicate that people are moving from here to here. So you can put the parameter value. Actually, in reality, also, I can tell you, in reality, when we develop the real system, real modeling, real disease modeling, there we will see there are many parameters which are not known at all. For those we have to estimate. How to estimate that? There is some procedures we learn in the later classes, maybe next class or after that. Actually, how to estimate those parameters. That is called model calibration. We have to find those parameter values and we can put this parameter because it is known. Means by experiment or by any method we can't measure that rate. How many? What is the rate from U to L? You can only actually estimate those parameter values, and we can guess. We can assume that this could be this. The rate could be this. But there is no direct method of, or experimental method of measuring this number. So you can put this number. We have already learned about that lambda, that S to I. So you can put the lambda here from U to L. You put the parameter lambda here. Okay, no need to parameterize. You don't know the value parameter value right now. So for the others, you just put. Do you need time? 5 minutes or you can we can discuss. If you want, you need 5 minutes time to think, then you can take.
I had one more question.
Yes.
In TB, I mean, TB is a long disease. But if we look at disease like COVID, where we can have like these patients who are right now susceptible, and they might develop a risk of infection. But if these susceptible patients are dying at at a number which is a good enough figure, how do we know if they're not dying of infection, or if these people are dying, how do we change our model to exclude the non-COVID deaths in these patients?
Very good questions. And after answering actually these questions, you will get the answer by yourself. If you can solve this, automatically you will get the answer. And the reason is, the short answer is the death rate among infected patients and natural death rate would be the rate is much varied actually, wide variation on that. So average lifetime is say 70 years. If we assume that average lifetime is 70 years, that means death rate from average natural death rate is 1/70 per year. Now we are changing the rate for TB. We are changing the rate in terms of year because it is lifelong infection and long-term infection. It is not that not like COVID. For COVID, we can transfer this rate. We will use this rate as per day. But for TB, it is per years. So natural mortality rate is 1/70 per year. Whereas if you think about that TB death rate, that would be much higher. 1/70 means 0.015, I think. Right, 1/0.68 means 0.015. But if you see the death rate due to TB, it would be around 0.3 or so. The rate is much higher during the disease, during infection period, means if someone is infected, but natural death rate is much lower. But you solve this, then you'll get better clear answer, means better clarification after doing this, after solving this.
Okay.
So which parameter will be, which is easy, just solve. You have to put the arrow, of course, from U to L, L to I, and I to R. There should be arrow. Now we have to, where to put the value of mu. There is a mortality, I said, means according to these informations, you have mortality. Death, the case fatality rate is given. That means people are dying from the infected compartment. So where to put mu, right now. At the beginning, I showed that introduction of mu. Mu should be from the I box, right? From I, there is people are moving, means that could be corresponding to the case fatality rate 50%. So and the other dates, where do you put? Means other, say average lifetime, lifetime without TB is 70 years. How do you put that rate? You have to give some rates to all these boxes, because anyone can die. Anyone from these boxes, anyone can die due to natural death rate, not due to TB death rate. Anyone can die. So all boxes will have some, means something which is going out from all these boxes. We can put some arrow from U outwards, it's going out from U, going out from L or I or R. So that will be the natural mortality rate.
When we talk about case fatality rate, that is probably active TB patients.
Yes.
Or it is
Yes.
active plus latent combined.
Not latent.
That
Case
is,
fatality means latent
it is
means,
from active TB patient.
Yes. Actually, latent TB rarely died. Means no one dies from the latent TB. Means we can say them they are dying naturally, not due to TB. The bacterial load is not that high that they will die.
Okay.
People are dying only from the active TB. So I don't know how many students are present right now in this classroom. And I'm not getting any response from any one of you, except one or two. Please speak out. So let me put the arrows first, then ask you. Is this looks fine? Again, the question.
Yes, sir.
Structure
Yes.
looks fine, right? Here mu0 is considered natural death rate for average lifetime without TB is 70 years. That is mu0. So first tell me. So tell me what would be the value of mu0?
1/70 per year.
1/70 per year. That is the value of mu0. That's done. One part is done of these questions. Now, next question is which one will be easier to Devaraj Patel. Please don't do this. So, okay. I don't know whether it is been shared or I have to share it again. Can you see my screen?
Yes, sir.
Yes, sir.
Yes.
Okay. Tell me, the mu0 is fine. Mu0 will be 170 per year. Now the other rate parameters, you have to find out the other rate parameters. Which one is easier?
Sir, over here in I, will it still be mu0 or will it be a different mu? That will be the CFR, right?
Good
Yes.
question. Actually, we will be coming to that point. Yes, you are right. So it is not only mu0. Mu0 should be there. Natural death rates among I compartment should be there. But along with that, there is additional thing. That would be the actually give you the 50% mortality rate. Case fatality rate is 50%. So additional mortality should be introduced in the I box.
Sir, why additional? Won't it only be mu TB?
Actually, yeah. Ultimately we'll do means mu0 will be replaced by mu TB. We usually do that.
Okay, sir.
Mu0 would be replaced by mu TB. Just to distinguish these two, I have shown is together in the same box. Means mu TB would be much higher than mu0. Yeah.
When you say that mu0 will be replaced by mu t, is it because mu0 is very small as compared to mu tb, or you are
Yes.
adding? Okay.
So I'm not adding separately. You can add the different ways you can model. It is not harm that then the rate would be according to that. So you can write mu0 and mu TB separately. If you want, you can replace mu0 by mu TB also. That depends on you. But whatever you write, you have to have that have to full these conditions that case fatality rate should be 50% from that box. If you write mu TB only without mu0, then the mu TB should be such that case fatality rate is 50%. If you have both two arrows, mu0 and mu TB, then accordingly you have that the value should be adjusted according to that, right? So if you can write if you write mu TB, then what would be the value of mu TB? If you write mu0 and mu TB both together, then what should be the value of mu TB? Actually, you have to find those values, those numbers. You will give me these numbers right now. Already you have given the number for mu0. Mu0 is 1/70 per year. That is for sure. That is done. The other rate parameters.
So mu TB is 1/3 per year.
Yes.
You have already estimated that mu TB equal to 1/3 per year. What does it mean? How do you get that?
So it's
Since I don't know, means I have not solved that yet. That's why I'm asking you.
So
Sir,
won't it be 50%, like 0.5
Hmm.
mu TB?
Hmm. Mu TB, okay, you are saying mu TB equal to 0.5. And
Yes, sir. I
someone
thought
said
gamma will be 1/3 here.
yes. Earlier someone said 1/3. That actually gamma would be 1/3.
sir, but CFR is mu upon mu plus gamma, right?
Yes.
So from there, if we calculate mu TB, it will come out to be 1/3.
It could be. It is possible. It is very possible. And I coming to that point now. Next is the most important point. But now you know the value of gamma. Gamma equal to 1/. Mu0 is confirmed. Mu0 is 1/70 per year. Gamma is confirmed. Gamma is 1/3 per year. No confusion about mu TB, but you are almost right because mu TB you have to estimate mu TB from the concept of case fatality rate. Case fatality rate, we said that this is 50%, means 0.5. 0.5 equal to mu TB upon mu TB plus gamma, right? As per your calculations. Now, according to competing hazard rate, it says that case fatality is 50%. means 0.5 equal to mu TB by mu TB plus gamma. And if you put the value of gamma equal to 1/3, so you will get mu TB equal to 1/3 per year. That is perfectly correct when you don't have the symbol mu0 here. If you don't write mu0 here, that mu0 from I box, then that is completely correct. That is correct answer. Then you should not write this arrow and this symbol. But if you write mu0 and mu TB both together, then the mu TB rate should be, what would be the mu TB? I am writing on my paper, so you can try it. So mu TB means case fatality rate would be mu TB divided by the total outwards means people's outwards rate actually, gamma plus mu0 plus mu TB. Means at the denominator, 3 terms will come. From the I box, the going out means mu0, mu TB and gamma. 3 rates are going out from I box, right? So in this case, if you want to keep mu0 as it is and mu TB in that model, then the case fatality rate would be mu case fatality rate means due to TB actually. Mu TB divided by mu TB plus mu0 plus gamma equal to 0.5. Clear?
Yes, I got it.
So that's why the first answer was correct. If you don't have mu0 here, if we remove this mu0, instead of mu0 you are writing mu TB, then to fulfill that 50% case fatality rate, the answer is correct. But if you keep mu0 and mu TB both together, then the answer is slightly wrong. But the answer would not be much different. And the difference would be very less because the reason is mu0, it takes around 70 years to, means 1/70. The number is very low. Means denominator, that number compared to other numbers, that number is very little, very less actually. So there hardly that the result will change hardly, means there very less change in mu TB, that number estimate value, but that is more accurate. Now the last hurdle is to find out that to incorporate that means three assumptions. The 3 informations have already been incorporated in the model. The last one is this one. 10% lifetime risk of getting active TB. From this information, you have to find out the value of R. Lambda, you can estimate the value of lambda. You have to find out the value of R. So how we'll do that? Any idea? Except you two, other people should say something. How to estimate the value of R? The information given is 10% lifetime risk of getting active TB. What is the meaning of this sentence? 10% lifetime risk of getting active TB. Lifetime risk means if the people may die lifetime in the whole life, the duration is around average is 70 years. Only 10% will be developing the active disease. That is the meaning of that. The 10% lifetime risk of getting active TB. All people, the remaining people will be staying in lifelong, means 90% people will be staying lifelong in the same box, in the L box, but will not develop the disease at all. This is the meaning of lifetime risk. So here, if anyone can answer, I'm telling you, means I'm trying to explain this now. So again, you have to use that for any rate of transitions, you can use the concept of competing hazard. Competing hazard tells you what percentage or what proportion of people are moving from that box to the next box. Here I am saying the 10% lifetime risk of getting active TB. That means 10% of L is going to I box. similar to that 50% case fatality rate. 50% are going to die from that box, means going out from that box. The same way, you can estimate that only 10% are going to, means to the R. R should be such that the 10% people are moving from L box. So to find the value of R, the formula should be R upon numerator is R, denominator is R plus mu 0. That should be 0.1. Is it okay? R by R plus mu 0 equal to 0.1. Because 10% people are going out from that box, from L box in the lifetime. So R by that means the same concept as you have that competing hazard. R by R plus mu 0, that would be 0.1. Then from here we know that mu 0 value, put the value of mu 0 equal to 1 upon 70 per year. Then you can find out, you can estimate the value of R. Is it clear? Any doubt?
Can you explain, like, can you summarize it once again?
Yes, sure. Why not? So you understand the concept of case fatality rate, right? Case fatality rate, the means you have one box here, L box here. Pupils are going out from this box in two different ways. One is those are developing symptom, means active disease, or those are dying from this compartment. Two outwards force is acting in this compartment, in this box. One is R and another is mu 0. Mu 0 gives you the lifetime risk, means at how many days it will take to die. That from the mu 0 compartment, we can have some idea that if these pupils are not going to the I compartment, if R equal to 0, then people will be dying at a rate of mu 0, which is 1 upon 70 per year. That's fine. Now, the possibility is that person can die, either die with at rate mu 0, or they can develop, only some percentage of them will develop active disease at a rate R. So now from the concept of competing hazard, that gives us the idea what percentage is going out from, means percentage and rate that corresponds to the competing hazard. Here there are one proportion is going to I and another proportion is going to, say, another box. If we put here M, death. So mortality M box and I box. There are two probability, either in R or in M. Means I or in M. So now to reach to I, the rate at which it is reaching to I is R upon R plus mu 0. Means there are two ways of going out. What are the total rate is R plus mu 0. At that rate they are going out from this L box. Right. Among them, what proportion is going to I box is the R proportion, means not proportion actually. We are going to find that value, means 0.1%. Sorry, 10% means 0.1. That 0.1 equal to, that means the same way the way we estimate that case fatality rate mu RT, mu TB. We'll use the same concept here. The recovery rate or developing symptom, the rate is the same. The competing hazard, you have the competition between R and mu 0. Out of these, how many are taking this path? How many are taking this path? Total would be always constant. R by this rate would be R by R0 plus mu and mu 0. And this rate would be mu 0 by mu 0 plus R. If we add up these two rates, that will give you the 1. Because the number of people going out from some compartment is going to add some another compartment. So the rate of all these rate going out rate would be the same as the input rate. So I should write these equations here. Otherwise, let me go back to the previous slide. I don't know whether we have those expression here. No, it was in the last lecture actually, that competing hazard. So we can see from here, it's at least. So do you understand case fatality rate?
Yes.
Why mu by mu plus gamma? From that box, from the infected box, there are two arrows. One was going to that mu, means to the recovered box, means R box, I to R. The rate was mu, sorry, gamma. And the other peoples are going out from the box, means dying from the I box. That rate was mu. So case fatality rate means what percentage of people are dying from that. Case fatality means how many are dying from that box. What percentage or proportion? Actually, in proportion, we write in proportion. What proportion are dying from that box? That we write as mu by mu plus gamma. If you see the structure again here, the simple structure, there are two paths. Either they can go follow this path or they can follow this path, mu or gamma. Now, case fatalities means people are moving from this means dying means from here to how many are going to die, means follow this path. The rate is mu by mu plus gamma. That will give you the percentage. What proportion of I is dying. Similarly, what proportion is going to R box? Can you estimate that value? In the same similarly?
Yes, yes.
That would be gamma by gamma plus mu. You recall the first class lecture, means we explain these things.
Yes.
So gamma by gamma plus mu would be the recovery. Means there are two, means some proportion is going up, dying means is coming to another box here, and some proportion is going to the R. What proportion is going where? That would be determined by these two parameters, mu and gamma. So what proportion is coming here? If I ask you that what proportion is coming from I to R, would be, we can say that not gamma proportion, gamma is the rate. So gamma by mu plus gamma proportion is going out from this box or to R box. And how many are dying means what proportion of I is dying is mu by mu plus gamma is dying from this proportion is dying from this box. The same way, the same principle we use here. Here. So what proportion is coming from L, what proportion is coming to I, and what proportion is going to for death, contributing death. But as per this information, what proportion is going to die is not given. Already you have given that death rate is given, but what proportion is going to die means it is not given here. But it is said that 10% of L is going from L to I. That is given. So if 10% is going from L to I, that means R should be such that the 10% of L is coming from here to here. So R by total outwards from L is R by mu 0 plus R. That would be 0.1. Is it clear now?
Yes.
So from here, as you know the value of mu 0, you can easily calculate the value of R.
Yes.
Okay, good. So then this is the complete structure for simple TB model. But now we have another term that the parameter value we don't know is the lambda. How many are getting infected? From this information, at least we don't have any idea about lambda. What is the value of lambda, which gives me from transition from U to L? It is not given here. And the other thing which is shown here, which I have not mentioned before, is that B. It is not that everybody is dying from, as we consider that everybody is dying from all these compartment. So we should assume that some people are also of course, are means some birth we should consider here, right? People are entering in these compartments. If people are moving, if you're dying without this birth, then what would happen? If you run the model, gradually all people will be dying after a certain time. After 70 years, within 70 years, everybody will be dying, maybe within a few hours. Everybody will be dying. So the system will be collapsed. So to keep the system alive, you should have some birth rate, not only death, but we have to introduce birth rate. So birth normally we introduced in the uninfected compartment. So infected compartment, we never introduced birth rate here, somewhere here in between. So we usually introduced birth rate here in the uninfected compartment. So that if you have constant population model, then birth rate should be adjusted in such a way that death and birth is same. Sometimes we do that. So we want to total population to keep the total population constant. We had to adjust the value of B in such a way that U plus L plus I plus R will remains constant whatever time period we are estimating these numbers. Because then if we assume that these many people are dying from this box, so if all the deaths are entering in this compartment again in the U box, that means total population would remains constant. Means what is the death rate and what is the birth rate, that will compensate to give the total population. But in reality, what we do that birth rate is different, then death rate is different. If you want to introduce the population is growing. If you think about the Indian population, it is every year it is increasing around 1.2% or 1%, 1 to 1.2% is increasing. So for that, we have to, if we want to model that, then we have to choose the value of B in such a way that it compensates with mortality rate, and then it will show the increase in total population by 1.2% to match with the reality. So you can do that easily. So good. If you learned up to this, then you are almost there to structure any model, any compartmental model. Now the major infectious disease modeling. We learned up to this. That force of infection means from previous structure already I have described this susceptible, infected and recovered compartment with lambda is called constant force of infection, and the recovered period according to that we will have that recovered at gamma. And the equation, governing equation would look like this. But in reality, for these assumptions, what we said that lambda is constant. At a constant rate, people are moving from S to I. But in reality, that does not happen. The reason is once people are moving from why people are moving from S to I? Because this is that if you can see, if you think about infectious disease, if for non-infectious disease, fine. For any non-infectious disease, if we think about cancer or any other diseases, only this compartment would be fine, means I to R, and with that rate, and we can model those diseases without considering any lambda or susceptible population here. We can model them. But for infectious disease modeling, we have to introduce this lambda term or force of infection. This is called force of infection. This force of infection, though in the earlier example we consider that is constant, putting some constant value, we can simulate these things. But in reality, that is not constant. The reason is this actually is determined by the number of infected people at a certain time. How many are infected? Say after 10 days of initiating some disease, number of infected population in a society or in a city is 10. Now gradually what would happen? Susceptible people will be infected from these 10 people. They are infecting susceptible people, and then they are becoming infected now. Now 10 would be, say, after a few days, 10 would be 15, then it could be 20, or gradually the I compartment will increase. Therefore, if number of infected people are increasing, then automatically susceptible people will be decreasing. And as infected people in a city will increase, the probability of getting infection to other people will also increase. So that means lambda is not a constant. Lambda is time dependent parameter. Lambda will change over time. I should say not time dependent directly. Actually, that would be determined by how many are infected at a certain time and how many susceptible populations are there at a certain time point. Actually, lambda depends on these two factors, means how many are susceptible population at a particular time and how many are infected population at a particular time. Both actually will determine what will be the value of lambda. So usually we write lambda equal to beta times I by n. What is the lambda is proportional to, means force of infection. If we say the lambda, if we named it as force of infection, we say this force of infection. Force of infection is proportional to how many infectious compartment or what proportion of population are infectious at that moment. Lambda is proportional to that number. How many are infectious at a certain time? If suppose you have 1000 population, you remember that mosquito that model that Ross has developed, one box with 1000, one village with 1000 population and one only infected initially. Instead of one infection, if you put two infection initial value as the initial infected population, then automatically the second day the rate of spreading the disease would be higher instead of when if infected population is 1. Means it is proportional to that proportion of infectious population. So I by n actually represents the infectious population, proportion of infectious population at a certain time. This is one, I by n. N is the total population, there is no death. So I by n is the infectious population at that time. So lambda would be proportional to the we equate that, then there will be some constant. Beta is a constant. This beta is called transmission rate that varies from disease to disease. So lambda, we replace all the earlier lambda by the rate beta times I by n. That means now we can replace this. This is called rate of infection. This beta is termed as rate of infection. How quickly the infection spreads from one single infectious person to the next. It actually effectively the number of infectious per day, infections per day when everyone else is susceptible. Means we can define this way. How can we define beta? Beta is called rate of infection. Lambda is called force of infection. Beta is called rate of infection. You just remember this terminology. Lambda is called force of infection and beta is called rate of infection. And lambda equal to means force of infection equal to rate of infection times what proportion are infectious at that time. So lambda varies with time, but beta doesn't vary. Lambda varies with time because infected population is changing over time. This dynamical model, we saw all these figures that it's going up and coming down. So accordingly, I by n is going means it will go up and down. So lambda is not constant. Lambda varies with time, but beta, which is disease specific, that is constant for a specific disease. But again, earlier I said that lambda, we can't measure lambda. Actually, we can measure lambda if we know that beta value. But beta is actually not measurable quantity. We have to estimate the beta value. So that the set of contact, I mean the beta, what determines the value of this beta. This is the contact rate, how the contact rate between different groups, susceptible population and infected population, how they are contacting each other, how they are mixing each other. Accordingly, that could change. And infectiousness of the disease, that actually determine the beta value. For COVID, say for TB. For TB, I know that beta value is around 10 to 15 or so. But that I'll come to that point later. Means the injection rate is 10 to 12. Means one individual can infect around 10 to 12 people during their disease course. That is the meaning of that, physical meaning of that. Now beta, we have to estimate the beta value. We can't measure it directly. So now if we rewrite these equations, instead of lambda, we put beta I by n. Yes, yes.
Is there any relation between the beta and the R0?
Yes, we are coming to that point. R0 and beta has a direct relationship. We'll come to that point. We measure that way.
Okay.
There is an indirect way of measuring beta. And
Okay,
again,
okay.
there is no direct method of measuring R0. That is also difficult. So anyway, we'll come to that point. Now I am coming to that means basically production number or R0. I am coming to that right now. So now we have the equations didt equal to. So I think you are okay. You are fine. I am continuing speaking at least about 2 hours, over 2 hours right now. So I think this is okay. So that I can finish this talk within 15-20 minutes. I'll try to finish this. Again, I will repeat next class. In next class, something if there is some doubt or other things. Or you can write to me. I will be happy to answer. I gave my phone number to all of you, but I didn't get any call from anyone else. Or you can give me a call from there. So the equation for I didt equal to this, right? This is clear. You have no doubt on these equations right now.
Yes, you can.
This is
continue.
actually SIR model. This is called SIR model. You remember in the first class I showed that McKendrick and Carmack, they developed first SIR model. This is their model actually. From their model, we use that lambda and gamma. They have used this terminology, so that's why we don't want to change this terminology. Everyone is using the same structure, same terminology here, lambda and gamma. So beta is I by n into minus gamma. This is called SIR model. This standard SIR model. And sorry. Please mute yourself if you don't want to. So annoying. If you someone don't want to continue, please you can leave it. I don't have any restriction that you have to stay here. I'm not counting anyone's head or anything. If someone is interested, please listen, or if you can leave it. You are free to go anywhere. Please don't disturb this way. So now, up to this, the equations are clear, right? This is called SIR model. And the main two parameters here in the SIR model, we have two parameters. You see, there we say in mathematical term, we say these are variable. S, I, and R are called variable. Parameters are lambda and means instead of lambda, we can say beta and gamma. There are two parameters. One is transmission rate, another one is recovery rate. So I'll go rapidly. Already I have explained these equations. The assumption behind this model, all models have some assumptions. What are the assumptions behind this model, SIR model? We assumed first assumption is the populations are homogeneous. Means in the S box, the people who are there in the S box, all people are equally they have the equal probability of getting the infection. It is not that someone is more infectious than the other. We consider that all populations are homogeneous. In the I group, all populations are homogeneous. Everyone has the same risk of developing disease. Everyone has same risk of recovering, of dying. Or all these things are homogeneous in the each box. This is the assumptions one. Second one is well mixed population. All saturated people have the same risk of getting the already I mentioned that. And the population is closed population, means total population remains constant. If we that means S plus I plus R equal to N. Total population remains constant. If we plot now again this is will be your task actually. You will develop the equation, you will write the equation, you will write your own code and try to write the equations and to get this figure out. How S, I, and R looks like, and your task will be based on these things only. So whatever practical session, whatever assignment I will be giving, based on these only. If you these things are clear, you will be able to answer those questions. So I is increasing and then how it is decreasing. And from here you can measure when the peak would occur. If one infection is introduced somewhere, then after how many days the peak would occur, when this will disappear, the disease will disappear. Everything you can estimate from this simple model. For example, I was thinking to give you this example to do it, but you can do it yourself. The same type of just changing different value of beta and gamma. Earlier, you have in some example I have given there I showed that if gamma changes, then how the scenarios would change. Now you can change both two parameters, beta and gamma, with 1 million population, and you can see you can just play around. It means how the epidemic will look like with different values of beta and gamma. And the most important thing that I am telling you from the beginning, that you have to interpret the result. That is the most important thing. What does it mean? If we get some result, you have to understand what is the meaning of this. From this figure, actually what it is telling is that epidemic occurs with beta equal to 0.5 and gamma equal to 0.25. The epidemic occur means there will be some peak and they will be going down. If there is a flat, if this is flat, then there is no epidemic has occurred. For what value of beta, there will be no epidemic. You can estimate this by numerical simulation itself. You can check that, you can play around. So for 0.5, this epidemic occurred, means people are infected and then going down, and some people are recovering. And the peak is reaching at the 56th day, means when the epidemic would reach the peak, you can estimate from here. What other information you are getting? At the peak epidemic, what percentage of population are infected? You can count this number here. You can count this number at the I group. Then you can tell that this many people are infected. From here, actually, around 15% of the population are infected. If you check the number, you will find that around 50% population are infected at the peak epidemic. By the end of epidemic, about 80% of the population has been infected and recovered. Here, that means at the end of epidemic, around 80% will be recovered. You can count these numbers and how many are there. So this interpretation is important. Just put this value and try to interpret the data, whatever your observation from these figures, from this diagram. I'm not going through this in details. By changing different parameters by different rate, you have to do this exercise yourself. These some example figures how it will look like. Say for a constant big gamma 0.1 beta, by varying beta equal to 0.1, beta equal to 0.2, 0.7 or 1.5, how the epidemic curve, that I curve, this is red one, is changing. So if beta is less, the epidemic peak is lesser, but if beta is high, the peak is the peak is higher. And you can notice the other thing, other important thing. So that means beta transmission rate will determine you, will tell you how big the peak would be or epidemic would be. The other important thing that is coming out from this figure, if you look at carefully the time course, time of peak epidemic, you can see something different. See from each figure. Say for this figure, when beta equal to less, peak epidemic is less, but it is occurring around 150 days or 130 days. The peak was occurring in 150 days. But here, if beta is higher, beta equal to 0.7, peak is of course it is higher, and it is occurring also rapidly, not 150 days, but around 30 days or 25 days. It is the peak is occurring. If beta is much higher, then the peak would be occur much rapidly. It will reach the peak, and the peak value of course will be much higher than the previous two. So this kind of, and for beta equal to 0.1, see there is no we didn't see any I. S is remains as S. I is means I is 0, R is 0 forever, and for that means beta equal to 0.1. If transmission rate is 0.1, there will be no epidemic. No epidemic means it is not. It does not mean that
if some infection introduced in a village, if we introduce some infection in a village, that does not mean there will be an epidemic. So there is a certain threshold for beta for which the epidemic would occur. Even if we have some beta value, if the recovery rate is much higher, then there will be no epidemic. You will play with this terminology, with this rate parameter, and see what is happening and what.
Sir,
Now, yes.
If we have to compare, let's say the second wave of COVID-19 with the third wave of COVID-19, can we qualitatively comment on the beta and gamma, like which wave had a higher beta or which wave had a higher gamma, or is it not?
Absolutely right. Absolutely correct. Means for my knowledge, what we have estimated actually, for the second wave, beta was around 2.5 or so. But for the third wave, for the first wave, beta was around 1.5 or 1.6 or so. For the second wave, beta was around 2.5. But the third wave, actually beta goes high. But the problem, beta was higher than the second wave, but the infectious, the mortality rate or case fatality rate has reduced because the variant was new variant. For the third wave, we have Omicron variant. Omicron was less fatal than Delta wave. Second wave is called Delta wave. In India, second wave is called Delta wave. There, that is much fatal, and there are more symptomatic development. Means the symptomatic people infection was much higher in second wave than third wave. Third wave actually asymptomatic was much higher, and mortality was lower. But of course, you can compare beta with the peak height and beta. You can compare. That is different. Okay.
Okay.
So if you want to go in details, means after doing this course, if you go to some of my papers, means already I referred all these papers, or not only my paper, any paper, you can see this comparison, how it changes. You can easily look at least basic things you can see. How beta is changing from first wave to second wave. Those are given there. You can easily compare actually with this information. Now, another important terminology is basic reproduction number. So basic reproduction number means from a infected people, infected persons, how many would be the secondary infection? Secondary infection from a infectious person means, or of course he is infectious, he or she is infectious. So how many will be infected from a single infected person if everyone is susceptible in the population? That is called basic reproduction number. All people are susceptible. Now we have introduced only a single infection. Now, then how many will be infected in the next step? In the next, yes. Say one is infected from this example. One is infected. Now, if this is for during this disease course, the day he or she was infectious, during that period, if he or she infect 3%, then we can say basic, and where everybody is susceptible, equally susceptible to the disease, then we say that R0 equal to 3. Basic reproduction number is 3. Or in the next step, how many people will be infected? This is actually exponential growth. You see, from 1 to 3, then everyone would be can infect another 3 persons. Here 3, 3, 3. That means in the first generation, this person infect 3, this person infects 3, and the second generation, these 3 people actually infect 9 people. So if you go in the next 9 to 3, 27 in the next step. So gradually it will increase rapidly. Means you will see that the growth will be exponential growth. So here we say the basic reproduction. If you plot this will looks like this. Here R0 value, we can say that basic reproduction number when everyone is susceptible. So R0 equal to from the data itself, you can tell, if you know that all the information that a number of people infected from one infection. So this is the average number of people can be infected from one infection. So R0 value is 3. from this figure, from the diagram, it is easy. From the data, if we plot these things, means from the number of cases in different generations, if you have sufficient data at the beginning, at the starting of during the start, say for first wave, when it was initiating in January, then for first few days, if we collect all this data, if you know that all the information that how many are infecting in India, then you can plot and you can estimate the value of R0 at the beginning. But it is very difficult. It's very hard to get individuals data, how many are really infected. So we always use another method to find the basic population number of R0. But roughly we can estimate from here as well, from the data itself. What is the rate? How many are getting infected from this curve itself? If we feed you the exponential curve data, then what value will give you that R0? That is actually 3. But the way of this is the definition of basic reproduction number. Already I said the average number of secondary cases caused by a single infected case if everyone is susceptible in the population. If R0 is greater than 1, that means the epidemic is growing. This is gradually increasing over time. But if R0 is less than 1, that will extinct. The disease will cut within few days. So now from this experiment, someone was asking me about the relationship beta and R0. So from this, I have just, can you guess, I have written only 3 possible scenarios relation between R0 and beta and gamma. So can anyone guess what could be the actual scenario? What should be the value of R0? R0 can be beta into gamma. Beta is transmission rate and gamma is recovery rate. Or R0 should be beta plus gamma, or R0 should be beta by gamma. Can anyone guess?
Is it beta into gamma?
So this is your guess, right? R0 means actually beta is actually giving you the how fast the infection is growing, right? And gamma is giving you the information how rapidly they are recovering, right? Now, if R0 equal to beta into gamma, that means R0 would give you the how fast, means it is a combination effect of course, combination effect of beta and gamma. Means both are proportional to, it seems that R0 is proportional to beta, R0 is proportional to gamma. If constant, this is say 1. Is it true? R0 is means R0 is also give you the how rapidly it is the disease is going to increase. What do you think? Will give you the result? Means is it proportional to beta? Means beta is giving you that how rapidly it is increasing, but gamma is not giving that way. So R0 should not be directly proportional to gamma. Or the second scenario, R0 equal to beta plus gamma, that would not be true. We'll come to this how we will estimate. Means there is some method how to estimate these things. I'll coming in the next slides. So R0 equal to beta by gamma. Beta means R0 will be proportional to beta. R0 is inversely proportional to gamma. If recovery rate is much higher, then R0 will be, of course, it will be slower. R0 will be slow, less. But if transmission rate is higher, then R0 will be higher. So let me show you those expressions, then I will end for today's session after this. So we all know these equations now. We are now familiar with this set of equations. dsdt equal to minus beta I by beta is by n, or didt equal to beta is by n minus gamma I, and drdt equal to gamma I. Beta is infection rate, r equal to recovery rate or removal rate. Okay. Now concentrate only on the single equation. For the middle one, how infection, we want to look after how infection is going up and down. That actually determined by the middle equations, means di dt. We want to look after that I, how I is changing over time, right? So pick up that equation only. Here, if we look the middle equations, that DIDT would be positive. Means if infection is growing, the condition for infection to grow would be beta is by n minus gamma I equal to greater than 0. That means beta is by n should be greater than gamma I. DIDT should be greater than 0. If it is greater than 0 and positive, actually, this should be positive if the infection has to grow. So the condition for infection to grow is beta I by n into S greater than gamma I. Clear? If you reorganize this, then beta S by n greater than gamma. Right? Are you listening to me? Or everybody has gone? I don't know.
Yeah, we are listening. We are listening.
Okay, okay. Is it clear? You can respond, unmute and respond without. If you don't have any music system behind you, then you can unmute and you can talk to me. And no issue.
Yes,
So-
sir, this is clear.
So beta I S by n greater than gamma I. This is the condition to disease to increase.
Yes,
Just reorganize this beta S by n greater than gamma. If you put gamma here in this side, then beta by gamma into S by n greater than 1. This is the condition for disease to propagate. Now think about that initial stages of the disease. When there is only single infection, if we introduce one single infection in a susceptible population, that means we can assume that S by n is almost 1 because everybody S equal to n. No other component, means everybody is the total population is n. If n is large enough, then S equal to n at the beginning. So we can rewrite this as beta by gamma greater than 1 in a completely susceptible population. So this is the condition for disease transmission. And disease will grow if beta by gamma greater than 1. Now we actually represent this beta by gamma transmission rate by recovery rate as R0. So R0 equal to beta by gamma. This is the basic reproduction number. Now you can relate in the other way also. You can think this way also. Beta is transmission rate and gamma is recovery rate. If transmission rate is higher than recovery rate, then the disease will grow. The disease will increase. But if transmission rate is less than recovery rate, then the disease will die. R0 would be less than 1. If R0 is less than 1, then if you will go this condition and it will die out, means it will be negative and it will die out. So at the first part, when beta is greater than gamma, means when beta is greater than gamma, the disease will increase. But if beta is less than gamma, the disease will decrease, means it will die out. So R0 will determine, R0 is a parameter which, if we know that parameter value, then we can say that disease will persist, disease will continue, or disease will going to die out, or disease will increase. I'm repeating the definition again for the basic reproduction number of secondary infections that is produced by a single infected host during its entire infectious period in a completely susceptible population is called basic reproduction number. Sometimes it's a basic reproduction number, sometimes it's few people say basic reproduction rate. Both are okay because those are those terminologies are used. Means which one is correct, I would not say. Number or rate, basic reproduction number or basic reproduction, both are used actually. I can cut anyone if you like. If R0 is greater than 1, we say that this is epidemic situation. In epidemic condition, when the infection is going up and up, that is called epidemic condition. R0 will be greater than 1. But R0 equal to 1, that situation is called endemic situation. The disease will persist for a long time, but there is no ups and downs. You can see that is going up or something. So it will persist, means beta I by S means number of people they are coming in the I box, number of people they are going out from the I box. If that is same, that means infection at a certain time, if you measure, that would be remains constant over the time if R0 equal to 1. That is called endemic situation. In some diseases in Africa, say for some malaria in some countries in Africa, they are endemic in situation. Means always year-wise you look after that number, slightly it goes ups and down, but almost is steady over the years. So this is the situation of endemic situation, means endemic disease. And if R0 is less than 1, irradiation is possible, means number will die. For COVID at this stage in India, R0 is less than 1. But this is the concept of R0, basic reproduction number. There is again another but. At the beginning, when everyone is susceptible R0, the definition of R0 is fine. We can estimate the value of R0 by this methodology. But after certain time, people are not, everybody will not be susceptible. So the susceptible people is reducing over time, right? They are going to the recovered compartment or I box, and through I box, they are going to the R box. So gradually, that is time dependent function, means that variable. S is gradually changing over time. So we define again R effective. That time we use this term R effective, not basic reproduction number. Instead of basic reproduction number, we use effective reproduction number. That is equal to R0 times S by N, which is time dependent function again. That varies as susceptible population is increasing, the R effective value. Susceptible population is decreasing, R effective is gradually decreasing. So R effective equal to R0 into S by N. For different diseases, R0 value means this is the range, means you can say specifically that this is the value we can say, but we can give some ranges. These are from some famous book of Anderson and May. We just pick up these numbers. For different diseases, what is the value of R0? What could be the value of R0? As I said, this COVID was not there. When the book is written, when the book got published, this information was not there. So COVID was not there. You can put the value of for COVID R0 value is around from 1.5 to 4. So R0 value for COVID. We can add this up with this. So this is your assignment. I will share these slides and you will have this assignment. How does R effective vary over course of epidemic? What do you notice about the connection between the change in R effective and the epidemic curve over time in relation to R effective? When does the epidemic peak and starts to decline? You can say all these things from the figure from R effective. If you draw the R effective and R, then you will answer these questions. I think this is my last slide. There is something, some other slides also, but I am dropping here. I'm stopping here. There are some vaccination and other things. I will come to these points in the next class. So I will say up to 39, up to slide 39. I will share to everyone in the group, and you have to go through the slide. Of course, if you have any doubt, you can ask me. You can write to me. You can call me, or also. The other assignment would be solve these problems. For many problems I have not solved here. I showed some figures. Also, the results where I have shown in the first or second problem set. I think I showed some results, but you try to do yourself if possible. And that is the main part actually. If this is concretized, if these concepts are clear, then there will be no issues on developing model in the near future. Yeah, if you have any questions, now I am stopping here. Let me know.
Sir, for
Yes.
for the TB, the national goal is to eliminate TB by 2025. Is the R0 value less than 1 for TB? And how much time does it take from eradication to elimination? Can we comment on this using R0 number?
Actually, R0 number for TB, for some diseases, R0 is not important. For the diseases which is like COVID, where it is going or polio or influenza, their R0 is important factor because we see the ups and downs very rapidly. It occurs within a few months or few days. It goes up and goes down. But for TB, as the disease is for long lasting, we are not much worried about R0 value. What is the R0 value? And from R0 value, we don't try to decide what is the factor, what is whether it is possible to reduce that, what is the target in by 2025 or 30, whether it is possible to reduce that on the incidence number by the time. It is not important for TB. And the other factor is the reason is that as TB is long-term disease and there are multiple factors which can actually influence the pattern, that incidence pattern or number of new cases for the TB. Suppose populations are means all population. At the beginning, I told you that these models are used for normally for homogeneous population or some which is rapidly going up and down. For TB, of course, we use this model, but not focusing on R0 value, because R0 value, the reason is the other factors which is influencing TB is malnutrition. Say, people having in malnutrition are having higher risk of developing the disease. People who are smokers have higher risk of disease. Smoker or those are take alcohols, those have higher risk of developing the disease. So it depends on many other factors. Whether the people are having HIV co-infection is important. Then there is a chance of having TB together. So there are multiple factors, and as this is long-term disease, it is not that if someone has TB, immediately within 7 days or 20 days or within 1 month they will die. It is not so. So for this kind of diseases like TB, HIV, which are long-term disease, we don't focus on R0 value. And we can say that actually when we model TB, we assume that baseline is stable, means it reaches to the endemic level. Then we are trying to decline with that. Means it is almost following that R0 equal to 1. Then we are trying to decline it from that level. That is the intention for TB. Is it clear?
I have a follow-up. You said that there are dependencies on various other factors, which are mainly the social determinants of health. And
Yes.
the SIR model assumes that we are dealing with a homogeneous population that has equal risk of hazard. Do we modify SIR model to quantitatively include the social determinants of health for the modeling that we do?
Yes, in real system, yes, we do that. We will come to that point later on. We'll come. This is a very simple model I have started here. So when you see gradually, this number of compartment will increase whenever we will consider those things. Means you can divide the population into 2 categories. Say. So one is say for example, if we think about TB, that malnutrition population. In India, around 10 to 15% are having low BMI. It's malnutrition population. So for them, we could develop models in such a way that some group, means S can be divided into 2 categories: susceptible population or uninfected population into 2 categories. One group which has low, those are in the low BMI setting, and those are at normal BMI setting. Now we can propagate, we can develop the equation. The difference between these 2 groups is that from low BMI setting, the rate of transmission for developing from uninfected to infected would be much higher than the normal BMI setting. So this is the difference. This way, you can segregate all these different social factor, whatever social factor you tell. So according to their problem, we have to understand the problem first. Then we can segregate the model accordingly. Actually, in my current TB model, I can tell you that these are examples. I have given these examples up to 4 compartment, right? 4 or 5 compartment. I have shown you some examples. In my latest model, this is also SIR type model, differential equation based model. As I am incorporating all these different factors, depending on the questions, what kind of question I want to address, depending on how we pick up the questions, accordingly we divide the compartments. The latest model consists of more than 350 equations, means 350 compartment. Because of this, because of someone has TB, someone has TB plus HIV, someone has drug resistance TB. So if we incorporate all these things and someone has different stages of diagnosis, we can construct, we can segregate the treatment stages in different way. We can segregate that R compartment, means recovered, means here I am considering that recovering, those are recovering. They are not going back to the infected compartment again. They have some immunity, permanent immunity we have assumed here in these models. But in reality, that doesn't happen. And from the recovered compartment, people go back to the means relapse could occur. So people can go back and develop the disease again. So there are different compartments in the R compartment also again. So depending on that, we can of course we will use SIR model, SIR type model. We say SIR type model, but of course the model is much more complex and there are so many things, so many parameters. All these things has to be incorporated in the model to get the reality. Is that okay? Anything else? You can, if you want to look after, at least means if you will not understand at this stage, but you can look after those some of my papers on TB models. I try to see the supplementary papers, supplementary figures, because in the publications, all we give all this all the good journals actually publish only the results in the front in the paper, main paper, and all the detailed mathematical expression, how did he solve this, how what are the equations, those are given in the supplementary document. Whenever you will download a paper, I will suggest to try to find out that supplementary document and see and try to compare the model structure. Model structure could be given in the main paper, but other details is given always is given in the supplementary document. Okay, if you see, if you are interested, if you have much interest, you can of course go through this. You can explore this area, and you can see how it is done.
I have one last question. You said that in the TB model there were 350 equations. That means a lot of parameters were there. So you just use the ordinary differential equations for modeling the system, or you have other mathematical models like graphs and also to model it?
No, actually, model is ordinary differential equation. So system is ordinary differential equation, the way we have seen. But the problem in the main model, the other thing is being incorporated more. That is more complex. The reason is parameter. Whatever I am showing it right now, all these are constant parameter. For a particular value, gamma equal to 0.1, I am saying mu 0 equal to 1/70 per year. I am saying you. These are the examples I'm showing you right now. But in reality, those parameters are not constant. Those parameters, we always consider some distribution of those parameters set. So mortality could vary from say for example, recovery rate. Recovery rate, the example I give is 0.1. 10 days is the recovery time. So 0.1 is the recovery rate I told you before. But if instead of that, if we say that recovery time could be from say someone can recover in 3 days, someone can recover in 15 days. So the recovery period, the recovery rate could be 1/3 to 1/15, or 1/15 to 1/3, within that range. And that too, within that range, as well as that could follow a distribution pattern. This could be uniform distribution, means where the or it could be some following some Gaussian type distribution. So you can assign those parameters from a distribution function, means so those things. That model, that's why I use, means for my TB model, I use Bayesian statistics, Bayesian modeling. So SIR model main structure is same, but the other thing means Bayesian statistics been used to capture the uncertainty of all these parameters and the target estimates. So this is different. Otherwise, the main structure is same. Whatever you have learned today, if you can capture properly, then you will learn the basic structure. There is no issues in constructing a model. Then how to run these things and other things you have to learn. Gradually you will learn those things. How to estimate parameters. So these many parameters are not, many parameters are unknown. So you have to estimate those parameters as well. So those unknown parameters you have to estimate. So we'll learn later, maybe next class, some basic technology, how to estimate that beta value or unknown parameters from for model fitting. Anything else?
Thank you so much.
Thank you for your patience. Last 15, 16 people are there still. Okay, and if you have any question, anyone can write me. No worries. Anytime you can write. I told you. I'm repeatedly saying so.
Yes,
Okay.
sir. Thank you, sir.
See you in the next class. Maybe next class will be taken by Professor Kollani, and after that, I'll be taking the class. Okay. Okay. Good evening now. See you in the next class. Bye.
Thank you, sir.